I am the Chief Product Officer at JuliaHub. I'm probably the only Chief Product Officer that spends this much time thinking about floating point ranges. So this is what I'm going to talk about. Floating point ranges, why are they hard? Can we do better? So why are floating point ranges hard? Consider this innocuous looking range, 0.1 to 1.7 with a step of 0.2. Let's, try to generate the values naively, the most obvious thing you would possibly do. So, you put your start, 0.1, plus integer multiple of the step and, the correct length, which I just figured out by hand, and oh, oops, okay, we get very messy looking numbers. Those are not the values we actually wanted. All right, so why this is happening, this is actually the source of 99% of confusion about floating point, is that 0.1 actually means this kind of nasty number. It's, every floating point number is of the form integer times a positive or negative power of 2. So, every fraction you're approximating is you're finding something of that form that's as close to the actual value 1/10 as possible. In this case, 0.1 is slightly higher than the actual value 1/10. 0.2 is slightly higher also. 1.7 is slightly smaller. So obviously you can't take a thing that's bigger than the true value plus a thing that's bigger than the true value and get a thing that's smaller than the true value. It just doesn't work. If taken at face value, these values, they're just incoherent, right? Like we don't have a workable range if we take them literally. That's normally what we do with these things. Like if we evaluate sine of 0.1, we don't actually compute sine of 1/10. We're not guessing that the user actually meant 1/10. What we say is, okay, well, that float value, even though we write it as 0.1, actually means this. We're going to compute the sine of that and then round it back to float. That's what we do. That's normally what we do. It's a sane thing to do. But in this case, it's incoherent, so we can't do that. Okay, so sadly, we need to do some amount of guessing here. Each value that we're getting has a bit of wiggle room. Yes, it has a true value that we often use, but also there were a bunch of real numbers that would round to that number. So any of those would actually be a valid interpretation. And so the question is, can we pick real numbers for all three of these inputs that agree with each other and actually hit the endpoint, and which all round to the correct values. Here's another example just to show some more nastiness. So this is another case where the true values are off of what you expect them to be, and you see that this is partly to show that our current implementation is not perfect, right? We do get this earlier example correct these days, but we don't get this one right. We don't hit the endpoint correctly, and then the midpoint of this range should be 0. It is not 0. It is 4.3 times 10 to the 9th. That's a lot. That's very far from 0. That's not the same thing. Okay, and this is a similar thing where the true value of this floating point number is these nasty things, and then if we put the little bit of the wiggle room due to the epsilon of the float, that's how much wiggle room we have. So what we really want to do is say, are there some integers in these ranges that we could pick that would make this thing work? And obviously there is, because that's the thing you had in mind when you wrote the range. But the question is, how do we do it algorithmically? How do we actually figure that out? Here's what we do now. We guess what A colon S colon B means. We compute the length by doing a division and rounding. So if there's going to be a length, that's what we think the length will be. Then we try to rationalize A, try to rationalize B. So by rationalize, I mean consider the interval of numbers real numbers that round to that, or rational numbers that round to that, and pick the simplest one. And there's an algorithm for that. It's actually very cool, very clever, but you don't need to know about that. There is an algorithm. And then we compute given those rational endpoints, what would the exact step be? And then we see if that actually rounds to the step we were given. And if that checks out, then we've got a good interpretation and we can just go with it. If that doesn't work, then we have to fall back to the literal bad interpretation, and we get, you know, these kinds of results. So it would be nice if we had something clever where this worked more of the time or worked all of the time. That would be amazing. One of the issues here is that, you know, when you rationalize A and B independently, you may not get an answer that actually, you know, can be made to work. You might need to consider them together to get a correct answer that actually is workable. All right, so let's formalize things a little bit. We'll view float inputs as intervals because that's more convenient mathematically, and that's like the set of real numbers that they could have been. So I write, you know, capital letters for the intervals, and I use minus and plus for the, you know, the low and high ends. So a rational interpretation of a range is a triple of rational numbers that are in the appropriate intervals that you were given, and such that the start plus the length times times the step is equal to the endpoint. So we actually hit the endpoint exactly for some n. We don't know n. We're not given n. I'll refer to n as the length here. It's not the length in the sense of it's the number of points you get, but it's the number of steps, and it's more convenient, and it's nicer usually. For example, in this one, you know, the actual length as a collection of values is 2e6 plus 1. You're like, no, I want 2e6. That's the thing I'm interested in. The grid unit. So this is if you have a rational interpretation, you can take the GCD of those rationals. So it's the greatest common denominator, and the definition there is just that these ratios are integers. It's the biggest value such that those are still are integers. And then those grid ratios always have a GCD of 1. They're always coprime. Okay, so the question is, how do we pick from all of the infinite interpretations? If a range specification is feasible and not degenerate, like empty, you know, 1-point intervals, then there's an infinite number of interpretations, and how do we pick a good one? This is the whole problem. And good one here means, it's weird, it's kind of definitional, like we get to define what it means to be a good one because nobody's giving us a definition, but we want it to match intuition. And we need it to be computable. So this is sort of the pull and push of this whole thing, is like we want something that agrees with what people intended, but also we can reasonably compute it. Okay. So one possibility that, you know, I was chasing for a while was the simplest grid unit that would make it work. And this is equivalent to computing some intervals for things, and then finding a denominator that simultaneously rationalizes them both, which turns out to be a very interesting but also very hard computational problem. And one thing I realized later after chasing that for a while was that tends to violate invariants that you actually really want to hold for this. And what I mean by invariants, I have to talk about transformations first. Here are some transformations you could do to an interval. You could scale it, so just multiply all of the things by some real constant. You could translate it, so that doesn't touch the step, but it does touch the start and the stop. I've changed the order that I'm writing A, B, and S here, sorry, but you'll follow. So that makes sense. You know, if you translate it, certain things should be the same, like the length shouldn't change, you know. The length shouldn't change for either of those. That's sort of like a hint of what I mean by invariance. And then there's this last one that it took me a while to sort of hit upon. It's this concept of refinement. If I cut the step in half, it shouldn't really change the endpoints, but it should just make the length twice as big. And for various reasons, we're only interested in binary refinement. If you allow arbitrary refinement by arbitrary integer constants, you end up forcing weird prime numbers into the length, and that's not what you want. But with 2, it's safe. It's actually quite good, and it's a nice property to have. So here are the invariants we end up wanting. So length should be scale and translation invariant. And I've written this in Julia syntax, but it's actually a little bit misleading because, you know, of course, if you multiply the floats here, you're not going to get exact invariance because there's round off with the multiplication. But what we're actually talking about is translating the exact mathematical intervals. So if you scale the intervals and you have a reasonable algorithm, you know, in the math world, in exact arithmetic, then it should give you these same answers. In floating point arithmetic, this wouldn't give exact answers. But if you had, for example, if you scaled by something that had no error, which is only multiples of 2, powers of 2, but then it would actually work. So translation also. Now the ratios, what I mean by ratios is those grid ratios. So if you return the tuple of grid ratios of your interpretation of a range, the grid ratios shouldn't change when you scale or do binary refinement. And in particular, the grid ratios don't include the length. So when you do binary refinement, of course, it changes the length. And here's the relationship we want for the length, is that if you cut the step in half, it should double the length of the range. Okay, well, so with those invariants, I spend a bunch of time noodling and figuring things out, and versus, let's look at these invariants versus the simplest rational approach. So the rationalized function, it does, it finds there's a unique simplest rational in any interval, which is actually a cool, deep mathematical fact based on something called the Stern-Brocot tree. And it's how our current range interpretation works and how the rationalized function works. But it's terrible it doesn't commute well at all with scaling and translation, even mathematically, right? Like it's not just a floating point issue. When you look for the simplest rational in an interval and then you scale that interval, you do not get the scaled version of the simplest rational. And same thing with translation. It totally messes with things. So this turns out to be, this is bad. Using this like if we use the simplest grid unit approach, we would like totally violate our invariants left and right, which is, it's both like undesirable, but also the real reason it's important is that those invariants tend to be true of the interpretations that people intended, right? That's the real reason we care about them. It's not like, oh, these nice invariants hold and math is pretty. It's, okay, the thing the person had in their mind tends to respect those invariants too. So if we have an interpretation that respects those invariants, we're more likely to find the interpretation that the person actually wanted. So I developed an algorithm for this. It's extremely hard to compute efficiently, and like I said, it violates the invariants badly, so that was a dead end. But I learned some cool math. All right, so lo and behold, I'm just gonna give you the algorithm, and I'm gonna try to explain what each of these steps means. It has 13 steps. All right, so first of all, if 0 is in the range of steps, then the range is infeasible, because you can't have a 0 step and go anywhere. If this is just one of those things where like these types of computations don't work out if the sign is negative, so flip the sign, make sure S is positive. If n is now you compute the lower bound on n, lower and upper bounds on n. So this is like the feasible length of the range, because we don't even know the length of the range. Remember in the beginning we computed b minus a over s and then rounded it? Sometimes there's more than one integer that could be in that. So rounding isn't always the correct thing to do there, unfortunately. So what we have to do is compute this. I think one of these should be a ceiling and one of these should be a floor. I believe the one on the left should be a floor and the one on the right should be a ceiling. Yeah, so anyway, so you have the bounds on the possible integers. You compute this. If this range is empty, you have an infeasible problem. We actually do a thing for that. If it's infeasible, if you can't hit the endpoint, we just stop at the point before the endpoint that was given. So that's what you would do here. You would just be like, okay, well, I can't interpret this. I'll just take it literally and stop before the endpoint you gave me. So now in that interval n, you find the integer with the maximum number of trailing zeros as a binary integer. Now this is the first heuristic I came up with here. Because one of the things you're looking at is you're like, you want a nice n. right? You know? And what does it mean for it to be nice? And is there a version of nice that we can compute easily? So, you know, one of the things you have is like, well, yeah, it's like a small integer times a power of 10. That's often what you meant. Sometimes you also mean like a small integer times a power of 2. That's also another common thing. As it turns out, 10 is divisible by 2. Deep facts here. That's very convenient because what we can do is we can actually just look for the number with as many trailing zeros as we can, and we tend to get nice like multiples of powers of 10 and multiples of powers of 2 there. Just happens to be that these are the number systems we work with. If you're doing, you know, a small multiple of a power of 7, you're kind of shit out of luck here. Sorry, like it's just not going to work as well. But that's acceptable. I mean, this only kicks in the case where like the epsilons are really big. So a lot of the time there is only one integer in that you could possibly pick, and this kind of doesn't matter. Another nice fact about that is that there is a single unique integer in any interval that has the most trailing zeros. So that's nice. Binary, yeah. If we could do it in decimal, that might be nice too, but it's too inefficient. We want to do it in binary. And the good thing is that doing it in binary tends to get you the nice decimal ones anyway. Okay, so now we let p equal the number of trailing zeros of n. And then what we do is we take n and a and b, and we divide them by 2 to the p. So basically we lop off all the trailing zeros on all of those things. We shrink them down. And now we compute this q bar interval. And essentially what this is we're looking for the interval where our like a over b ratio could be, or sorry, a over s ratio could be. So we have those like grid ratios, and we're putting a bound on where the ratio a over s could be, the lowest and largest and smallest number that a over s could be. And then we're going to try to figure out what a over s is. But, and this is the thing, we've done it in this reduced space where we've divided by 2 to the p. And the reason you want to divide by 2 to the p is because of the refinement invariant. And this is a little hard to explain. I should have had a slide or something for this, but there were too many talks to prepare. So the finer your grid is, the more likely you are to sort of hallucinate the property you want of it, because it's just kind of like, oh, this thing happens to line up in a right place. So what you actually want to do, I put it as refinement because it's simpler to state the invariant that way. But what you actually want to do is you want to take your grid, and then essentially what you're doing when you're taking this dividing by 2 to the p is you have a grid, and it's got like a lot of steps, because now you know your ends, you know how many steps there are. And what you're saying is like, you know what, let's just make our steps bigger so that there's an odd number of them. It's the biggest we can do. We can make the steps without changing the properties of the range. And when you do that coarsening is a good way to sort of avoid hallucinating properties of the range. And it makes that invariant hold by basically saying, okay, whatever version of this I found, like let's suck out the powers of 2 to the p and then work in that, you know, maximally coarse version of the range, and then that's the properties we actually want. So there's 2 cases here. If that range contains integers, that's what this property says, is like, is there an integer in there? Then we just say that our grid ratio can be, you know, an integer over 1. So a over s can be an integer over 1. And that's what we do. We just say like, okay, we pick a to be the nicest integer in that interval, and we say s. And again, it's s, a bar, and s bar. We say that a bar and s bar, a is an integer and s bar is 1. Otherwise, we have, you know, this q minus and q plus. This q interval doesn't contain any integers, and we take the fractional part here. That f should have a bar, but it doesn't matter. and we find the simplest fraction in there. I actually think this is equivalent to finding the simplest fraction in the Q interval, but it's just easier. The numbers are smaller. So that's what we do. And then, whichever way we did this, we can get B. And so now what we have is we have our grid ratios, actually. So what we have is that we've essentially got our interpretation. We've got N, and we've got the math letters A, B, and S. And what we have is our interpretation is now alpha is A over S, beta is B over S, and N is N. And so we've almost got our range interpreted now. We know the ratios, but we don't know the actual grid unit. But we need to go back, we need to put those powers of 2 back in. This is just very mechanical. You just put the powers of 2 back in and keep it reduced. It's not a big deal. So now we actually have our fully re-expanded A, B, and S. We have our ratios. All right, so now we want to find the grid unit. And the way we do that is we take our intervals that we were given, and we divide by the integers. And now this is basically we have this interval over here and this interval over here and this little step interval, and now we're projecting those all onto the grid, and they should all overlap. If they don't overlap, you've got trouble and the algorithm is broken, but they should all overlap and intersect, and the true grid unit is in that intersection. So now you just have one interval, you find the simplest fraction in that interval, that's your grid unit. Once you have your grid unit, all of the values in we have the grid unit as like a rational, right? And so then what we do is we take it from a rational and we compute in double precision. So we don't just do one float division, we do like the float division and then like the error of that. So now we have the grid unit at high precision as a float. And we can do a fused multiply add to get any value in the grid, and it works. Like this actually gives you correct answers. All right, so let me do a very quick demo. Okay, okay, all right, so I have this function called lift range. Okay, so we have our range, and this is the example that works horribly before in current Julia. All right, so can we lift it with the new lift range algorithm? Da 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 da. Moment of truth. Yes, it works. And if we collect the values, they are exactly the values you want. All right. Another fun thing we can do is this is a subroutine. We can just ask what the range ratios were. And so what this tells us is that the length of this thing was 7, okay? And that the A integer is -3 and the B integer is 4 and the S value is 1. So now you know like the ratios of everything as integers, but I return them as floats because they have better range. And we can see this is actually like a horrible hacky version of the code. I really need to do a better version, but I ran out of time. I think this is the file. Yeah. Okay, so I will. It works with yeah, it'll work with any step range, and it doesn't really care about the fact that lengths have to be integers. This is the actual code. I mean, I'm not going to go through it. It's just like I'm just showing you the horror show. So that's the lift range part, but then there's the range ratios part, which is all of this nonsense. It's crazy. I think it can be made simpler and faster. But anyway, I have like 1 minute for questions. Does anyone have a question? All right.
How fast is it?
Currently slow, but I think it can be made fast. I don't think there's anything in there that's like horribly slow. Basically, what you do is what you want to do is take the floats, convert them to integer ratios with a floating power of 2 in there, and then do everything in integer arithmetic, and then until at the end you produce 2 floating point numbers. One more question, maybe?
Not sure if you're familiar with like posits or other like floating point alternatives, but will this algorithm generalize to those? Have you looked into whether that's like a good general solution for any given arbitrary number type?
Yeah. I mean, there's nothing floating point specific. The inputs are intervals of real numbers. The output is a rational number. So all the internal stuff is actually like not floating point at all. It's all done you want to do it in exact integer arithmetic. Okay, thank you.